And we move on with a presentation exploring quantum advantage for the German industry. And I would like to introduce Jonas Stein. Jonas Stein is doing his PhD at the LMU in Munich at the chair of mobile and distributed systems, focusing on research applications for quantum computing. And as a research associate at the Quantum Applications and Research Lab, he contributes his knowledge to various industrial projects, research, and teaching. In his talk, he will give us an overview of use cases, especially focusing on domains of logistics and production line management, and he will give us some clues how to integrate them into the industrial environments. So please come to the stage. The stage is yours.
Awesome. Yeah, thanks so much for this kind introduction. Maybe with this talk, I want to motivate everybody a little bit of what can be done already now with quantum computing and why it's meaningful and sensible to already look into that kind of technology from an industrial perspective, which is actually what we are doing in our project called QCHALLenge, which I'm the coordinator of. This project basically emerged from a student course that, by coincidence also, I teach at the LMU, called the QC Optimization Challenge, which we are doing since the summer of 2021, where every semester basically we gather around 20 students and some use cases from industry partners and implement and benchmark these on real quantum devices. Which is very interesting because now over the course of the time we really have seen already the hardware emerge and also new applications arise and new fields that are interesting for the community in general. Based from this student course, basically from this cooperation there, we came up with the project QCHALLenge, coincidentally having a similar name, of course, and came up with some project goals that we wanted to achieve. First one being, of course, low threshold access to quantum computing. So in the end, in industry, we want to be able to just use quantum computing more or less without even having to think about it, right? We don't want to figure out the quantum algorithm ourselves. In the end, it's just, it should be plug and play, basically. And with that, basically, we want to work towards a kind of readiness for quantum advantage. As soon as it's there, it should be just a push of a button away for the German industry to then also use that. And the focus there that we are looking into is production and logistics. And overall, of course, we are very eager to work towards strengthening the QC ecosystem that we already have here in Germany. And now to achieve these goals, basically, we came up with some things to do, of course, for this project. The first one being quantum applications that we want to explore. I think this is something that like every company in principle can do already today, and it's also, it's a time-consuming thing, and it's also very important that we already now look into it, because as soon as the quantum advantage is there, we want to be able to benefit from it. And if we don't know where to apply it, what is it good for? And for today, I've brought some small example, basically, of what we are doing there. But before that, I want to show some of the use cases that we are looking into, which are from BMW, BASF, SAP, Siemens, mainly centered around optimization use cases, but also some in the domain of quantum machine learning. So we have the standards there, like routing problems, scheduling problems, packing problems, which have been looked at for quite some time already now with quantum computing. But we also have some newer problems and coincidentally also finance-related problems, which will be one example that I'll dive in a little bit deeper today, being some kind of financial price prediction. And one interesting thing that you can do there is sentiment analysis, which is basically looking into the sentiments of people who are interested in buying things on the stock market, for example, and process these in the sense of we want to classify them to be rather positive or negative about some course, for example. This is especially important in the era of online social media and so on, where you can see here on the left side a tweet from Elon Musk where he proposed selling 10% of his Tesla stock, which is also, of course, something that we want to be able to automatically process, of course, because this influences the prices a lot. In the end, by the way, he did sell it. All right, and we want to look into this with natural language processing. The thing is, we all know the success from ChatGPT and other large language models, but in the end, they are very, very hardware consuming in the learning process. And we are interested in seeing, okay, can we maybe save some energy, for example, doing this in a quantum way? And in fact, there are many approaches out already, and some of these need grammatically correct sentences, for example, which is why we came up with a nice way of doing a benchmark, which just needed some data generation that we did coincidentally also with ChatGPT. We asked it to build a data set basically, and sentences came out like the stock market experienced a significant increase in value today, bringing positive news for investors. So we are using classical machine learning here to generate data for benchmarking quantum approaches, which is what we did next. Then we looked at two different quantum approaches. So on the left here you can see LSTMs or quantum LSTMs. So in blue, in blue basically the classical benchmark, and in pink you can see the quantum approach. And in this case, higher is better, so we are trying to learn something. The more close we are to one, the better we are predicting in data. And actually, we can see the quantum approach already works well, which is just some very small number of qubits that we needed for this kind of simulation. On the other hand, we also saw another approach, which is very much it's a little bit hyped in the quantum natural language processing domain, called DiscoCAT. Doesn't learn so well in comparison to that. So it's very interesting for us to see, okay, which are the algorithms that we can actually apply in the end, doing these kinds of benchmark studies. Okay, so we saw it compares well with the classical baseline already. We might be able to use this with lower energy consumption in the future. And other approaches, might need some more massaging until we can actually use them in practice. All right, if you're interested, of course, I'm showing some paper results here today. Feel free to look into them. All right, then moving on to the next point on our project agenda, basically is advancing basic quantum algorithms, which is a daunting task because quantum algorithms are quite complicated, but with some particular applications in mind, for example, there's a lot of potential to optimize how we use these algorithms, and in particular how we formulate those questions that we have for the quantum computer. One example is coming from optimization, especially for chemical processes, for example. We have some kind of functions where we are seeking for global optima, in the sense like minima and maxima, for functions that you can see here on the right side, for example. And these kinds of functions are typically modeled with some continuous higher order functions. And we asked ourselves, how can we use quantum computers to actually find these optima? And the question that we asked ourselves is, how do we tell the quantum computer how this optimization landscape looks like? And there are two basic ways to do this for these kinds of higher order functions. There's Cubos, which you might already have heard of, which is just a quadratic function in that sense. And there's also higher order functions, just polynomials of higher degree, basically. And if we compare those two approaches, we can see the Cubo has a way larger circuit, so a more complicated program in that sense for the quantum computer to understand, versus another formulation, which is the Cubo here on the right side, which is like the native way of giving in that problem. But historically, many people have used Cubo problems, which in this case turned out to be not so optimal, because if we look at the solution quality that we get out from both, so this is now using a quantum algorithm to solve these optimization problems and finding a minimum. And on the x-axis, we have like increasing number of steps that this algorithm is allowed to do. And there we can see with the Cubo approach, it takes way longer to actually find a good solution. And for the Cubo approach, actually, we find basically the global optimum in the end very nicely. So in this case, we see, Cubo outperforms Cubo. So we see for these kind of problems, this is the way how we have to talk with the quantum computer. Also here, feel free to look into the paper. All right, another thing that we are very interested, of course, in basically talking with quantum computers, in telling them what they should do for us, is how we encode data. And this is a substantial problem you might have heard of, the input problem for quantum machine learning, where we say, okay, once we have the data in our algorithm or in our quantum computer, we can do very cool things. We can achieve exponential advantages, but how do we even get there? And this question of encoding and then also processing data, is really fundamental. And this is why we looked at a very specific example here on how we can improve this, basically. There's a very famous algorithm out there here shown on the bottom, which is called the HHL algorithm in quantum computing, which allows you to, for some systems of equations, solve them exponentially more fast than is possible classically. And this algorithm has a very nice theory to it, but it's very hard to actually apply it in practice. And we wanted to benefit from all that nice theory, but still be able to maybe not in the next 2 years apply it on a real hardware, but sooner than possibly what could possibly be done with it in its original form. This is why we came up with a nice, you could say, approximation of a very big part of this algorithm, which takes a lot of qubits and a lot of gates, and which is also more fault tolerant, basically, and just replacing that section, which is actually just there for let's say processing the data, which comes out of this first box here. And by that, what we achieved basically is a rapid reduction in the number of gates that are required in that algorithm. So in blue here, you can see basically for some different combinations of number of qubits n and the polynomial degree that we want to approximate d, the number of gates here on the y-axis basically. And in blue, there's a naive version to do that. Then in orange, there's a slight adaptation by omitting some zero-angle gates that appear there naturally. And then in green, there's our approach, which basically shows that in some cases where you have a lot of qubits already, or a moderate amount of qubits, I have to say, and a high degree, there we can substantially reduce the size of the circuit that we are looking into, like really by orders of magnitude. So overall, we can see with this paper, there's a possibility to really speed up some of the already known algorithms that have a proven advantage, basically. So whoever is interested in looking into this, I'll have the talk on that today night, because Quantum Week is happening in parallel in Seattle right now. All right, then for the project agenda, basically this already brings me to how can you directly benefit from this, basically. We are doing all the work. We are looking into quantum applications. We are advancing some quantum algorithms. And then in the end, for this project, it's the goal to compile all that in a software framework that is usable, basically plug and play for everybody who is interested, and then also a roadmap for the industry, where we look into, okay, which algorithms are interesting, which applications are interesting, how should the industry proceed with that knowledge. Of course, this will happen more towards the end of this 3-year project, so in the next 1 or 2 years. But if you're interested, you can already look into some code that we have compiled in our GitHub. And whoever is interested in getting this roadmap first, feel free to message me, of course, to be informed. Then in the end, I just want to make a little bit of advertisement basically for all of our other projects that we are also looking into, which is just a small compilation here with those 5. Most interestingly, there's the Cocoon project, which is called Quantum Computing User Network, funded by the BMWK, which should be or is supposed to get a central hub for people to access quantum computing in Germany. So whenever you are interested in applying quantum computing to some problems in your own company, this will be a hub where you can access it, and there will be an online platform which is already being built now. And there are also other projects that we are working on that are looking into many different applications. For example, this BiQAR project, or also this QGrid project, which are also BMWF funded. There we are looking into optimizing clinical trials, for example, together with Merck in the BiQAR project, and how quantum computing can help for that. And also on the other hand, with QGrid and EON together, we are looking into how to optimize energy grids using quantum computing, and there's some really cool work coming out of that. Yeah, but overall, of course, we are just one small brick in all the quantum ecosystem, which is of course also partly done in Munich Quantum Valley, which we are also a part of, and also in the Planck project, which most of you probably already have heard of. All right, then I'll already hand it over to you guys for some questions. Thanks a lot.
Thank you very much. And looking at the time, I think we have still time for at least 1, maybe 2 questions. Are there any questions? Are there? Or are all the questions answered? Yeah.
I mean, if there are no questions, I will ask a more mathematical question. So I'm wondering why the Cubo is working better than the Cubo, although you're working like with higher degree polynomials. So I was wondering about that.
So the idea is basically that with the Cubo, we don't need as many qubits, because if you have a higher order function that you want to basically quadratize into a quadratic function, then you need some additional variables. And this blows up the search space, basically, and makes it harder to find a good solution just because the space you are looking through is just way bigger. That's our sense of why it's better, basically. So on the one hand, we have this bigger search space, but actually if you want to go into the detail, it's actually a trade-off. You need a little bit of a longer circuit for the Cubo approach, but it's using less qubits and getting better results.
So you're needing more of slack variables like to formulate the Cubo?
Yes, exactly. That's the main problem that we have identified.
Okay, thank you.
Great, thanks. So thank you very much for giving us these insights in this presentation. Give him a warm round of applause. And